In the diagram, P, Q, and R lie on a circle with center O and radius 12. The point S lies on OR. If POR is 135 degrees, the area of the trapezoid OPQS is closest to. Well, let's cut up this diagram a little bit. I'm going to draw a line like that, that's perpendicular, and then a line like that, that's diagonal, so this is perpendicular. Alright, so the good news is that when you do that, you are able to cut this into 3 equal triangles. All of these are equal. And you say, well, how do you know that? How do you know for sure that they're equal? Well, that's where the angles come into play, right? And also the sides, not just the angles. So, for example, this was 135 degrees, and if I made this into a right angle, which I did, that means this angle in here is 45. It's 135 minus 90. So this was a right angle, that's 90, so therefore this is 45. So that means this side and this side are the same. And then this side right here is the radius of the circle, which they told me is 12. And in a very similar way, you can do that for all the other triangles. For example, this is also the radius because O is the center, and then Q is on the circle. So that OQ is a radius, so I can label that 12. And in a very similar way, since that's just a diagonal, this is going to be 45 degrees, that angle in there. And then since this is 90, this is 45 degrees right here. And then the identical kind of story holds true for that triangle. 45, 45, and 90. So this is again isosceles, so that is equal to that in terms of the length. All right? So since this side is the same as that side, all of those sides that I have drawn this symbol are all equal. Okay? So I hope that makes perfect sense. And we also know that this side is parallel to that since we have right angles here. So all we really have to do is find the area of one of these triangles and then multiply it by 3, and we've got the area of OPQS. So OPQS will basically just be 3 times the area of one of those triangles. So I'll just write a triangle right there. Okay, so how do we figure out the area of the triangle? Well, I will label this side x, and this side, of course, therefore is x also, since it is equal. And then just use Pythagoras on that triangle to figure out x. So we have x squared plus x squared is equal to 12 squared. So 2x squared is equal to 144. X squared is equal to 72, and therefore x is equal to the root of 72. So 3 times the triangle, well, one triangle is 1/2 base times height. The base is x, the height is x. So this is 3 over 2 x squared. Well, x squared I just got was 72. So it's 3 over 2 times 72, and that is 108. Yeah. So number 23, the answer is C. In the diagram, PQRS is a trapezoid with an area of 12. RS is twice the length of PQ. The area of PQS is. Okay. So, first and foremost, we have to label this. RS, I'll call 2x. And that means PQ is just x, right? Because they are saying RS is twice the length of PQ. And then the area of a trapezoid, for example, if this is a trapezoid, and this is A and this is B, and top to bottom that's H, the area of a trapezoid is A plus B divided by 2 times H. So using the same formula, the area of the trapezoid here will be 2x plus x divided by 2 times H. Now H we have not labeled yet, so I'll put that in there. I'll label that in the diagram, top to bottom right there. So that's H. Okay? So I'll just label that. And they're telling me that this area is equal to 12. So this becomes 3x over 2 H is 12. I guess you can write it in terms of xh. 12 times 2 divided by 3. So xh is equal to 24 divided by 3, which is 8. And that's about as far as we can go there. Now they want you to figure out the area of triangle PQS. PQS. Well, triangle PQS is going to be equal to the full trapezoid, which is PQRS, minus this triangle right there, which would be QRS triangle. Okay, so PQRS we just figured out. Well, actually, they give us that in the question. It's 12. We didn't really need to figure out anything. But QRS we have to figure out. That'll be 1/2 base times height. The base is 2x, and the height is h. So this becomes 12 minus just xh. Xh we just figured out was 8, so this becomes 12 minus 8. And that is equal to 4. So triangle PQS has an area of 4. So number 22, the answer is B. A rectangular piece of paper, PQRS, has PQ equal to 20 and QR equal 15. The piece of paper is glued flat on the surface of a large cube so that Q and S are at vertices of the cube. Note that QPS and QRS lie flat on the front and top faces of the cube respectively. The shortest distance from P to R as measured through the cube is closest to. Well, we have to look at this very carefully and try to understand how to do this in terms of the three-dimensional aspect of the question. So first, let's do the obvious stuff. We know that we can label this pretty quickly, right? PQ is 20 and QR is 15. Now, this is a rectangle, so that means SP is 15 and SR is 20, right? It doesn't look like it because it's three-dimensional, but it's a rectangle that's been basically half of it is on one side of the cube and the other half is on the top of the cube. Now, what we can very quickly do is figure out the median. So what I mean is that distance right there. We can do that with Pythagoras pretty quickly. So that means that SQ squared is 15 squared plus 20 squared. And that is 225 plus 400, and therefore SQ will be the square root of 625, and that is 25 for SQ. Now this diagram, I'm going to start labeling this. So the first thing I want to do is drop a perpendicular from P all the way to SQ like that. So this is a perpendicular. And then I want to draw a line from T, or this, I haven't labeled it yet. I'm calling it T, I haven't labeled it. So this is T, this point right here, that it touches the line SQ. From that point, I'm going to draw a line to R like that. Now the reason we're going to do that is because, and you have to kind of think about this in 3 dimensions, when I draw a line from P to R, which is the required length, this triangle that I just drew in red is a right triangle. Okay? So I hope you can see that. So if I can figure out what is PT and what is TR, then I'm set. Because then all I would have to do is just solve PT squared plus TR squared is equal to PR squared. Like that. And that would essentially be how I would solve it. But I have to obviously individually work out PT and TR. Now, the next step in this question is a similar triangle comparison. And in particular, it's 2 triangles. And those triangles are triangle PTQ is similar to triangle SPQ. So those 2 triangles are similar because they have the same angles. For example, if that is theta, this is a right angle, and you'll see that SQP has the angles 90 theta and obviously 90 minus theta. And very similarly, PTQ, which is this triangle, also has the angles 90, which is this guy right here, theta, and of course a 90 minus theta. So based on that, we can compare the sides. That means that TQ over TP is the same as PQ over SP. And PQ over SP, well, those have numerical values. It's 15 and 20. So that means TQ over TP is, in lowest terms, 4 over 3. So what I can do is I can label them. I don't have a numerical value, but I can label them with a variable. So TQ, I can write 4x. And TP, I can write 3x, like that. And that is sufficient for me to figure out what is x, because I can use the Pythagorean relationship right here. Okay, so far so good. All right, so let's use Pythagoras now to figure out x. We have 3x squared plus 4x squared is 20 squared. So that means 400, and this is going to be 9x squared plus 16x squared, so that's 25x squared. And then if you divide through, x squared will be 4 times 4, which is 16. Therefore, x works out nicely to being just 4. So that means that this 3x is actually a 12, and that 4x is actually a 16. Okay? So far, so good. So now, I'd like to keep that diagram in the screen, since it really helps us. At this point of the question, we have to now use something called law of cosines. And the law of cosines will help us figure out TR, because TP we've already got. TP PT right here is 12 squared. So that's part of the puzzle to figure out PR squared. The other part of the puzzle, of course, is TR. To figure out TR, we have to use the law of cosines. And we're doing it on this triangle right here, TRQ, that triangle. Law of cosines on triangle TRQ. Okay, so here we go. TR squared is equal to 15 squared plus 16 squared minus 2 times 15 times 16. And then we need an angle. So I don't want you to get confused. So what I'm going to do is, instead of trying to explain it on this diagram, I'm just going to draw that rectangle flat like that. And the rectangle that I've just drawn is the same one, P, S, R, Q, like that. And then, of course, I'm going to draw the line SQ to sort of illustrate that we have cut it in half like this. And then let's label this with the dimensions. And I label T, I draw that line PT. And then let's also draw in what we know so far, that PT is equal to 12, and that TQ was 16. And since, if you remember, SQ we had figured out earlier was 25, that means from here to here is 25, and therefore that means ST must be 9, since TQ is 16 and 9 plus 16 is 25. So now what I want to do is go back and try to continue this law of cosines. Remember, I've got to put cos of some angle. So cos x, right? Or whatever you want to call it, alpha, some angle. But that angle, I wanted to draw it on this flat diagram. Since I'm interested in figuring out TR, there to there, the angle that I'm really looking at will be labeled here. Right here. This will be your alpha, this angle right here. And that angle is the same as this angle right here. Alpha right there. Okay? And that's just because these are parallel lines And if you draw that, you'll see that those two angles must be the same. And the good news is that the cos of alpha, we don't even need to figure out the angle. We can just get it using the sides. Cos is, of course, adjacent over hypotenuse, so it would just be 9 over 15, or 3 over 5. So that's it. We've got everything we need. So let's continue with TR. TR squared, therefore, would be 15 squared, 225, plus 16 squared, 256, minus 2 times 15 times 16, 480, and then the cos of alpha, which is 3 over 5. So this is going to be 481 minus 288, and that is equal to 193. And that's it. Now we just put it directly from here to here. That's why I wanted to keep it in the same page. So TR squared is 193. And there we go. That means PR squared would be 193 plus 144, which is 12 squared, which is 337. And therefore 337 square root would be PR. And if you take the square root of 337, you get approximately 18.35. And let's see here, 18.35 is closest to choice E. PQRS is a parallelogram with area 40. If T and V are the midpoints of sides PS and RS respectively, then the area of PRVT is PRVT. That is the shape they want you to figure out the area of. Okay. First, let's draw some lines that hopefully will help us. I'm going to extend PS like that. And then what I'm going to do is draw a height from R down to that line. And of course, this is a right angle. So that red line is my height for this question, for this diagram. Now, how do you figure out the area of a parallelogram? It's basically base times height. Like that. In this particular parallelogram, the full one, this would be my base, and the height I've just drawn right there. Now, I don't think I know any of those values, right? They just give me the area. Okay, let me just plug that in there. 40 is equal to base, which is PS, times height. And so far, that's all I've been given, not much more than that. Okay, no problem. We'll keep that for later. Now, let's go back and look at PRVT. PRVT is what they want me to figure out the region, the area of. Well, PRVT is going to be half of the parallelogram, which is PRS, minus this little guy, this triangle, TSV, I guess. Correct? I hope you're convinced of that. So just to recap, PRVT is this region. How do we get that? Well, we take that big triangle and subtract from it this small guy. And when you do, you'll get PRVT. Okay, so PRS, first of all, which is PRS, is just half of the parallelogram. Parallelogram has an area of 40, so half the parallelogram will be 20. Right? Now we have to concentrate on TSV. TSV is not a parallelogram, it's a triangle. So that will be a different formula. Similar, but different. 1/2 base times height. Okay? Now, the base of this triangle is TS. So put that in there. And the height, well, the height is from here to here. Now, they tell me that V and T are the midpoints. So since V is the midpoint, if you drew a line from V to H, it cuts H in half, meaning this is the same as that. So the height of that, which is from there to there, is essentially going to be half of H. So this height is h over 2. All right? So now we got 20 minus a half. TS now, what's TS? Well, TS is half of PS because T is the midpoint. So this becomes PS over 2, and this is H over 2. So this now combining, we get PS times H all over 8. And then PS times H is 40. So we got 40 over 8. And then therefore this is 20 minus 40 over 8 is 5. And therefore that gives you 15. So number 24, the answer is C. The top section of an 8 by 6 centimeter rectangular sheet of paper is folded along a straight line so that when the top section lies flat on the bottom section, corner P lies on top of corner R. The length of the crease in centimeters is. Well, perfectly allowable. Take out a piece of paper and make that fold, and you'll be able to see the crease. And then once you have the crease, we can move forward with the question. When you make that crease, it will be something like this. That crease will be approximately something that looks like that. Then you can try it, right? I encourage you to try it. So what we will do is we will work with that. First thing I want to do is draw some horizontal lines. One here and one here, like that. And let's start labeling some things here. It's an 8 by 6, right? So this whole thing is 8 and this whole thing is 6. Now, the distance from here to here, that I don't know, so I'll just call that x. And these were horizontal lines, so this is going to be x. And this is x and that's x also. And therefore, this section in the middle is going to be 8 minus 2x. And yeah, that's pretty much all we have so far. But the reason I told you I encourage you to do this on a piece of paper is that you'll find that when you actually make that fold and have P come and land on R, you'll notice that this segment right here corresponds entirely to this segment from there to there. So if you were to draw, say, a line from this point to this point, you will see it matches entirely to that segment. It's identical. So what that means is that those lengths are the same. So since from here to here is 8 minus x, right? 8 minus x is from here to here. This is also 8 minus x. So I'll just put that in there, 8 minus x. So now we've got two Pythagorean relationships, and off we go. So the first one is this guy right here. That one gives me x squared plus 6 squared is equal to 8 minus x squared. And that's going to be 64 minus 16x plus x squared is x squared plus 36. The x squareds cancel, which is very good. And that's 16x, and then 64 minus 36 is 28, and therefore x will be 28 divided by 16, which is 1.75. Okay, pretty good number. Now our next Pythagorean relationship involves this triangle, and the crease is what they want, right? So that is the crease there, so I'll just call it C for crease. That Pythagorean relationship is as follows. It's 6 squared, right? Because from here to here is 6, plus 8 minus 2x squared is equal to c squared. So substitute x equals 1.75 into this, and we get 36 plus, that's going to be 20.25 when you square it, 8 minus 2x squared. And that's equal to c squared. And this is 56.25 is equal to c squared. And when you take the square root, you get 7.5. So the crease is 7.5, and that means number 22, the answer is C.